Let's talk about exceptions to the octet rule. Okay, so there are three exceptions to the octet rule. So far we've been learning Lewis structures, and we've seen that pretty much with the exception of hydrogen, everything else is obeying the octet rule. There are cases where the octet rule is not obeyed and still you draw a valid Lewis structure, except for there's no 8 valence electrons. So the three cases we're going to look at is, first we're going to write exceptions to the octet rule. So there are three cases. One is odd electron species. So the species out here is inherently, it's got odd number of electrons. So you can't get to 8, that's an even number. The other option is, the other exception is something called an incomplete octet. And the third one is the case of an expanded octet. Okay, so let's go ahead and focus our attention on odd electron species. So let's consider the case of nitric oxide. So let's go ahead and try to draw the Lewis structure. So the number of valence electrons out here for nitrogen would be 5. Let's go ahead and write, and for oxygen would be 6. You add them up, you have 11. See, that's an odd electron species. If you draw the Lewis structure, again, you can follow the honk rule, but in this case, it doesn't matter because there's only 2 atoms. So you just draw a nitrogen connected with the oxygen. And then let's go ahead, since we used up 2 electrons, we have 9 remaining. So let's go ahead and put them one by one on the oxygen and nitrogen. So that's 8, and then there's one more left. You can put that on the nitrogen out here, or you can put it on the oxygen like that. Okay, and both of these are valid structures. Okay, so as you can see now, before you kind of close the situation on this, a couple of things to keep in mind. This nitrogen has 2, 4, 6, 7 around it, and this oxygen has 2, 4, 6. So none of them have a complete octet. So you have to try to see if you can get at least one of them to have a complete octet. Okay, I'm going to erase this one for now so that we can kind of focus our attention on this. What if I take one of this lone pair and put that out here to make a double bond? Then I'd have something like this. There you go. And now this oxygen has 8, and this nitrogen has 2, 4, 6, still 7, right? Okay, now if I put one more out there, okay, then I could have something like that. So if I slide these two over and that, but then now this oxygen has 10. So that's not an acceptable structure. You can't have more than 10, more than 8, okay? So this would be the most valid structure for an odd electron species like NO. Now here's an interesting situation. So as you can see, there's 2 scenarios that can result from this final structure. You could also choose to put 2 electrons on the nitrogen and then have 1 on the oxygen. If you did that, it would be, let's say, it would be instead of this going here, you push, I'll just do it in red out here so you can kind of understand what's happening out here. So we can take a look at the distinction. If that came here instead, then you'd end up with something that looked like this. And then now, instead of the lone electron being on nitrogen, okay, we're going to still keep these 2 out here. You can put the lone electron on oxygen, okay? And so then oxygen would have 3 and 4, 7 electrons, and nitrogen would have 8. And these are all completely valid Lewis structures, and these are interchangeable. So therefore, these would be resonance forms, okay? Resonance forms. Now, what is true is that this oxygen still needs one electron, or this nitrogen still needs one electron. Therefore, this kind of a species is predicted to be unstable, okay? And because it is unstable, it's going to be super reactive. It's going to look for another electron from wherever it gets it to react to kind of fulfill that electron, okay? These kind of species with unpaired electrons, whenever you see unpaired electrons in any species, these are called free radicals. All right. Let's direct our attention to the case of an incomplete octet. Okay, so now first of all, when an octet is incomplete, it just means it has less than 8. Technically, we shouldn't use the word octet, because you should use octet only when there is 8, but because the octet rule is so popular, we just say the octet is not complete, so hence incomplete. So we're looking at less than 8. So take the example of BH3. If you look at BH3, number of valence electrons boron has is actually 3, and each of the hydrogens has 1 electron, so that gives a total of 3. 3 plus 3 is 6 total valence electrons. Now, if I draw the Lewis structure, I'd put the boron in the center, I'd put the hydrogens all around the boron. Let me just write this properly. And when I do that, I have 2, 4, 6. All 6 of those are used up, leaving no valence electrons left. As you can see, the hydrogens are happy because of the duet rule, but the boron is not happy because it still needs 8, okay? However, there aren't any more electrons, okay? So therefore, you'll have to stop at this, okay? So this is the Lewis structure of boron. You can go ahead and predict the geometry, which would be trigonal planar. And then the question about this compound would be, how stable is this compound? This compound is actually also pretty unstable. Okay, so because it needs 2 more electrons, it's going to look for any species that can donate its 2 electrons to the boron. Okay, and we see that happening a lot. Another example would be BF3, and you can kind of do the same thing for BF3. And if you just to cut a long story short, if you do BF3, you will end up with something that looks like this, a Lewis structure that looks like this, where the fluorines have complete octets, but the boron is still lacking. Okay, let's direct our attention to the next exception to the octet rule, which is the exception called an expanded octet. An expanded octet is basically a rule where you have more than 8 electrons in the octet. So this usually happens in elements that are in period 3 and below of the periodic table. So if you recall the periodic table, you have period 1, period 2, period 3. Up till period 2, you see cases of incomplete octets, regular octets, duets, and so on. When you get to period 3 and below, then what happens is you actually have a D level that is vacant and is very close in energy, okay, to the valence shell that you're trying to fill up, and therefore there are cases where the excess electrons can totally go into the D level, and that's what we end up seeing. Let's take a look at the example of SF6. Now, the valence electrons in sulfur is 6, and the valence electrons in each fluorine is 7. But since there are 6 fluorines, you multiply that with 6, so you get 42. So you take that 42 added to the 6, you have a total of 48 electrons to go around. Let's go ahead. We're going to put sulfur in the center, and using the honk 1, 2, 3, 4 rule, if you recall, the H also stands for halogens. Therefore, the fluorine is going to form 1 bond. So if you put sulfur out here, there's fluorine. Put fluorine out here. Here's another one. Here's another one. Here's another one, and here's another one. Okay, so you have all these fluorines. That's how many electrons already. 1, 2, 3, 4, 5, 6 times 2, that's 12, which leaves us with 36. So there are 6 fluorines, so each of them is going to get 6 lone electrons, so 3 lone pairs each. And there you have it. that completes the Lewis structure for SF6. As you can see, the fluorines have complete octets, but the sulfur in the center actually has 2, 4, 6, 8, 10, 12 electrons. That's an expanded octet. Anything over 8 is an expanded octet.